All right, so I want to talk for a minute about what to kind of expect on the test. Now, I've had a couple of quizzes, and I would say that the test will probably feel somewhat like taking, several quizzes, okay? So it'll be like just kind of a strung together collection of quizzes in some sense, okay? Typically, I do have like a true and false section or like a short answer section in addition to just working several problems. I will write the test so that it could be completed in 50 minutes, but I will give you, what is it, like 65 minutes or something like that. So you should have plenty of time to finish the exam. There's no doubt in my mind, okay? So couple of test-taking strategies that I would submit to you. At this point, I'm sure that you've taken a number of math tests, but one of the biggest mistakes that people tend to make when they take math tests is they'll get stuck on a problem and they'll stay on it, okay? So if you get stuck on a problem, skip it. Not forever, but for a while. And make sure that you work through all the stuff that you know how to do first, and then come back to the things that that are giving you trouble. Okay, so that's just a math test-taking strategy that is a tried and true method. Okay. So remember, all of the lectures and things are on the YouTube channel. So, I mean, if you need to go back and remind yourself of, some specific topic or maybe some examples that we worked through, all of that stuff is recorded. So hopefully that's a help to you. One thing I like to do to kind of help me remember what I should remember, although we can kind of recite this from memory, this is a good exercise, is I'll kind of open the book and go to the table of contents and read through the sections that I'm responsible to know stuff about. And in my mind, I'll sort of try to think about the type of problem that I would do from that section, okay? I'm not even actually doing any problems, but I'm just trying to think back over the material holistically. So I would go, okay, 8.1. Oh, that's like the tricky integrals section or whatever. I don't think it's called tricky integrals in the book, but in essence, I'll think, okay, yeah, right. That was the one where I sometimes was having to like multiply and divide by the same thing, or add and subtract the same thing, or complete the square. Sometimes I had to use like arc-trig stuff to kind of pull off what the antiderivative was. Yeah. I go, okay, yeah, that's right. I remember doing that. The second section was integration by parts. And then I would kind of in my mind imagine, oh yeah, integral of u dv equals uv minus the integral of v du, right? And I imagine maybe even the ILATE acronym, which when you read it left to right is telling you the priority for what gets put equal to u, right? Inverse, trig function, logarithm, algebraic, trigonometric, exponential. Not everything falls into those neat categories as we've seen, but that's just kind of a helpful thing for remembering what to do. Section 3, trig integrals. So powers of products of sine and cosine and secant and tangent. So we spent a fair amount of time on that, thought about different parity of powers. Remember the word parity. What does parity mean? What am I talking about? It's like oddness and evenness, right? So like, right, what we did kind of depended on whether the powers were odd or even in certain cases, right? In the case of sine and cosine, remember sometimes we had to resort to using so-called half-angle formulas, right? Sometimes they call them the power-reducing formulas also. By the way, I wanted to remind you Okay, so like the first section was the tricky integral section, and you had to remember a whole bunch of integrals from the past and bring them back to the present to use now. But if you go into, let me see if I can kind of pull this up, right. If I go in here, I think, let me just make sure I'm actually in here right now. Nope. You sign in, okay. Okay. So if I go to the book, right, what I'm doing right now is I'm basically going through the sections in the book, and so I'm kind of thinking, right, instead of, I call 8.1 tricky integrals, they call it basic integral rules, yes? But one thing I would submit to you is, if you go to the end of the book, there's this little thing called formula cards, okay? And on 2 pages, basically they list everything that we need for chapter 8, okay? So those formula cards include things like, here, let me see if I can make this a little bit bigger here. Okay, derivatives and integrals, by the way, so like the first line and the second, or the first part and the second part are just kind of going back and forth between each other. Of course, you just have the derivative version and the integral version below. But like in the slides from 8.1, I literally just did a screen grab from this right here. Does that make sense? So I can just put that directly into the slides. So you see all the arc trig things right here. So here's all these basic integral formulas we were making use of in section 1 of chapter 8. And by the way, if you go to the second page, you have this. Like, here's all those things that, and remember, here's the so-called power reducing formulas. Okay, I call those half angle formulas, okay? They call them power reducing formulas because they do end up reducing the powers, right? When you actually use them in the context of trig integrals. They have the Pythagorean identities here. They have the double angle formulas here, which we've been using. They even have the sum and difference formulas and the product to sum formulas. Like, remember, we actually used these. We used these at the end of section 3 of chapter 8, right? But those 2 pages basically have everything right there, and they have the nice little unit circle picture. I expanded upon that picture in the first quadrant there, and showed you what was really going on with some of those trig functions. Okay, so that was section 3. How do I get back to the actual table of contents? Oh, over here. Yes, sir.
For the trig circle, would you recommend getting a second diagram for the tangent function?
Well, the tangent, no. I mean, so remember, the tangent, like these are all sine and cosine values at various angles, yes? The tangent is just the length. Like if you were to draw the tangent line, let me draw a little picture here. Okay, so the tangent is this. Like if you draw the tangent right here, right? So this is the tangent of whatever that angle, that's the tangent of pi over 3. I mean, so you can see everything in that one picture, actually. Where's the cotangent? Do you guys remember? It was over this way, right? So if I were to extend that up that way, that would be the cotangent. This right here is the cosecant. This right here is the secant. Okay, so there was some nice geometry going on there. So this stuff right here was the cotangent of pi over 3. Okay. That was kind of the generic picture that I drew, but you can see everything within that one diagram. These aren't the graphs of sine and cosine tangent and stuff, right? The graphs look different, but this is just geometrically explaining what those lengths are, okay? So what about 8.4? Well, so 8.4 is trig substitution, and 8.5 is partial fraction decomposition, right? Those two tend to give students the most trouble in chapter 8, those 2 sections specifically. We skipped section 6 and we did 8.7 and 8.8. 8.7 was indeterminate forms and L'Hopital's rule, and 8.8 was improper integrals. Improper how? Can someone explain improper how? How were the integrals improper in section 8 of chapter 8? Right, so you either had the limits of integration being plus or minus infinity, or you had a problem with a point in the interval itself where the function was like taking off to infinity or something like that, okay? So that's how they were improper. And of course, L'Hopital's rule oftentimes helped us deal with that, okay? We talked a fair amount about indeterminate forms when it comes to limits. Yes, sir?
So for 8.7, the homework had us do L'Hopital's rule and solving using applications from chapter 1 and 2.
Oh, okay.
Are we going to be expected to know how to do that on the
Well, what I'm mainly going to be concerned with L'Hopital's rule is you can just compute limits with it when you need to. Yeah, that's my primary concern with L'Hopital's rule. Okay. And now, I mean, we've been using it again in chapter 9 as we've been doing limits of sequences, right? L'Hopital's rule has made an appearance again, and it will continue to make appearances over and over and over again. Okay? Okay, does that make sense? So this is how I study. I kind of go through the sections and I remind myself, okay, I remember doing that. And then what I tend to do is, like, you see these little review exercises? Like, these are great, okay? These review exercises are great. You just go in here and you say, oh man, how would I do these integrals, right? Now, the thing I like about this, or actually, like these ones, it tells you, this is telling you to do things from section 1 of chapter 8. Use basic integral rules to do these ones, right? This one right here, it's saying use integration by parts, like tells you what to do, okay? But I think later on, here, let me see here. I think later on they may just have a chunk of problems where they don't even tell you anything, okay? It's like these ones right here. See these guys? These don't tell you jack squat. They just say, do the integral, for crying out loud. Know what I'm saying? So if I were you, I'd practice those, because the nice thing about them is it's more true to form. I mean, typically you're not going to have some entity that comes in and says, hey, do this problem using integration by parts, right? You're just going to have an integral, and you're going to have to decide what in the world what tools do I have to actually deal with this, okay? So like, I think these problems would be good, like, review problems for you to kind of work through, because they don't tell you how to do the problem off the bat. Does that make sense? Hopefully. Okay. All right, questions on that? Yeah. There will be ones where I just say do this integral and I don't tell you like a specific technique to use. There will be others where I say do this one using integration by parts or something. But there will be examples of problems where I won't tell you which method to use. Does that make sense? Yeah. And there's some nice limits for you to evaluate. That's cool, right? Some improper integrals over here. Know what I'm saying? So there you go. I like the review exercises. It's just a kind of a tight collection of things for you to work through and practice. Those are some helpful sections at the end of each chapter in this book. Okay? All right, other questions that I can address. Let's do this one right here. Here, I'll zoom in big time. Watch this. Oh man, woo! Check that out. Okay? No guidance whatsoever. Well, what do you think we're going to have to do? Partial fraction decomp. Okay. Okay. So 3x cubed plus 4x over the quantity x squared plus 1 squared. Is that factored completely already? X squared plus 1 quantity squared. Can that be factored any further? No, it's done. Now, do I have to divide? No, careful. It's actually, the power on the bottom is actually the power 4 if you think about it for a second. Okay. So let's see. Let's 3x to the third plus 4x over that thing. Okay. Okay, so integral, all right, integral of 3x to the third plus 4x over the quantity x squared plus 1 squared dx. Okay, so what is the form of this going to be? Yeah, that's right. You have a repeated factor of x squared plus 1, so you have to count them up. Yeah? Cx plus d over x squared plus 1 quantity squared dx. So then the question becomes, what are these guys, right? What's a and b? What's c and d? You know, what in the world am I going to do? What we know is that if you were to bring this, like you could either multiply through by the denominator on the left and cancel stuff, or you could think about bringing that sum back to a common denominator by multiplying ax plus b by another factor of x squared plus 1. And you know the numerators would have to be the same. Okay, so you know that 3x cubed plus 4x, which is the numerator on the left, would have to be equal to what? Help me out here. Yeah, ax plus b times x squared plus 1, right, to bring it to a common denominator, plus the other thing, plus cx plus d, yeah. Okay, and I don't know. I mean, I'm always inclined to just collect terms. Okay, so if I were to multiply out that first thing, I would have a cubic term, wouldn't I? What would the cubic term be? Ax cubed. All right. What would the squared term be? What I'm doing is I'm just like, I got the cubic term by multiplying ax by x squared. And I'm also going to do this, and I'm going to do this, right? So what is the squared term? Bx squared. Okay. And what else do I have? Plus. I have plus ax, but I also have a cx. So overall, how many x do I have? Yeah, a plus c all times x. And then finally, the constant term is just b plus d. Exactly. And I stare at that little equation that I just came up with. I stare at it, and I say, well, all right, on the left, I basically had 0x squared, and I also had a 0 constant term, right? So I can compare coefficients. What are the okay, so like the thing that's sitting next to x cubed on the left has to be the same as the thing sitting next to x cubed on the right. Therefore, what? A equals 3. What about b? B equals 0, because after all, the thing sitting next, right, why is b 0? Well, because of this and because of this. Yeah? That's what's going on. All right. What does A plus C have to equal? Think about it. A plus C on the right has to equal to 4. But I know that A is 3. Do you know what I'm saying? So what's C? C is 1. Okay. And finally, what's B plus D equal? Okay, so B plus D is equal to the constant term on the left, which is 0, but B is 0. So what's D? Yeah, so D is 0. Okay, I have everything. Okay, so let's see. This is going to be equal to the integral. Okay, A was 3 and B was 0. So this is 3 over 1 plus x squared. I'm writing it that way on purpose, by the way. The x. Okay, C is 1. Okay, so it's going to be plus the integral of x over x squared plus 1 squared dx. All right. Oh, sure, 3x. Thank you. Good. So what do we do? Yeah, you can do a u substitution, right? On this guy right here, I could put like u equal to, so what would u be equal to? 1 plus x squared du would be 2x dx, right? So like x dx, this thing right here, x dx is equal to du over 2. Do you see what I'm saying? Okay. Okay, and then over on this guy, let's use w for this one, okay? W equals, same thing, x squared plus 1 dw is 2x dx. So x dx is dw over 2. Okay? So these integrals turn into what? Is it just going to be 3/2 the integral of du over u? Okay? Plus 1/2 the integral of, yeah, w to the negative 2 dw. Exactly. Okay. That's fairly easy to do. So let's see. I'm kind of working my way around here. So this is going to be 3/2. What's the antiderivative? What's du over u? What's the antiderivative 1 over u du? Logarithm absolute value of u. So it's going to be 3/2 logarithm absolute value of 1 plus x squared. Okay. Do I really need absolute value around that? Let's just be honest here. No. Okay. Now, what about the antiderivative of w to the minus 2? Negative w to the minus 1. This would be minus 1/2. Okay, minus 1/2. Oops, actually, I'm going to go like this. Minus 1/2, or minus 1 over 2, what w is. What was w? Okay, plus a constant. There you go. Okay. There it is. Questions? Questions on that? Okay, the partial fraction decomp, trig sub, those tend to give students the most trouble. That has been my experience. Okay, so just make sure you kind of have that sorted out for sure. Any questions on that? All right, well, let's see. Let's try another one here. Where were we? We were right here, right? Okay, I don't want to be this giant anymore. Okay. Let's see if we can see another one here. How would you do? Let's see. How would you do the let's see, 52. What would you do about 52? Any idea? Trick sub? Okay. Okay, that seems like it might help us. Let's see. So trick sub, let's think about that. All right. So it's just the integral square root of 1 plus the square root of x dx, okay? Not everything looks perfectly like the situation that we started with in trick sub, okay? So, all right, let's see. Let's try it out. So we want to do, what was it? The integral of what? Square root of 1 plus the square root of x dx. Huh. Now there's a 1 right here, correct? Right, so so which Pythagorean identity is in play in this case? And so it's like 1 plus tangent squared of t is equal to what? Yeah, that would work out nicely. But what I have here is 1 plus the square root of x, yeah? And I basically want that to be equal to the secant squared of t so that the square root sort of goes away. Know what I'm saying? Okay. So what does that, I mean, just stare at that for a minute. What does that mean the square root of x should be? Yeah, that's right. Okay, which really means that x is like tangent to the, interesting, tangent to the fourth. Exactly. And I kind of need that because I need to figure out what dx is. Ooh, what's dx going to be? 4 tangent cubed of t, right? And then I have to use the chain rule. What's the derivative of tangent? Times secant squared t dt. Beauty. Okay, so I can start subbing some stuff in here. Let's see what happens. It's going to be the integral. First of all, what is the square root? I mean, look, 1 plus the square root of x is secant squared. So what's the square root of 1 plus the square root of x? Let's not horse around here. What's that going to be? That's just secant of t. Okay. So that giant nasty square root just becomes secant. Okay. Secant of t times, okay, what's dx? Well, it's all that gnarly stuff, right? 4 times tangent cubed of t times secant squared of t dt. Okay. Let's clean this up. I can pull the 4 out. It's going to be the integral of, what do I have here? Yeah, tan cubed, secant cubed. Okay, and now we're going to be forced to remember some stuff from the third section, right? So what? What do I do? Say again. So, Kira, what did you just say? Secant tangent? Okay, let's see. Or integral, okay, so that's going to be tan squared of t, secant squared of t, secant t tan t. Okay, what are you thinking about here, Kira? Well, remember this right here, I mean, just to, okay, why did we do that? Well, because that is the derivative of what? Yeah, that's the derivative of secant, correct? That's the derivative of secant, yeah? Therefore, I should try to change everything into secants, which means I should change the tangent squared into secant stuff. Make sense? Okay, this is going to be 4 integral. So what's tangent squared in terms of secant stuff? And then this is going to be secant squared t. And this, right, Right. So then it's going to be, let me just write it in parentheses, secant t tan t dt. And we put u equal to secant t, so that du is secant t tan t dt. Okay? So this whole thing becomes 4 integral of, what is it, u squared minus 1 u squared du, right? Okay, which is 4 times the integral of u to the 4th minus u squared du, just by sort of distributing that thing through. And so what are we going to get here? What do we get? 4/5. 4/5 u to the 5th minus 4/3 u to the 3rd plus a constant. Okay, what was u again? Secant t. Okay, let's go to the next page here. So like overall, what we have is 4/5, the 5th power of secant, minus 4/3, the 3rd power of secant. Right? But we actually know what secant is, don't we? Does that make sense? We actually have secant raised to the 5th power and secant raised to the 3rd power. We know how to do that because we know precisely what the secant function is. Make sense? Sitting right there, it's the square root of 1 plus the square root of x. Okay? So let's kind of write out what this is on the next slide just so we have an answer here in the end. So the integral square root of 1 plus the square root of x dx. Let's see if I can remember. It was 4/5 u to the 5th minus 4/3 u to the 3rd plus c, and u was secant of t, or u was secant of t, and what was secant of t equal to? Radical 1, right? And I'm going to write it like this: 1 plus the square root of x raised to which power? Yeah, that's right. Okay. So what do we get? 4/5. 1 plus square root of x raised to which power? 5/2. Minus 4/3. 1 plus the square root of x raised to the 3/2 plus a constant. Look at that. Amazing. Apparently, when you take the derivative of that thing, lots of stuff is going to end up canceling. But there it is. I think that's pretty neat. Okay. Any questions on that? So trig sub can handle more than meets the eye, correct? I mean, sometimes it doesn't have to be like constant minus x squared necessarily. In this case, it was actually the square root of x, and we still forced the issue, yeah? So it's a pretty versatile tool to have in your toolbox for sure. Okay, questions? Questions about anything we just did potentially? Yes.
So, we ever see like the square root of 1 or like a constant plus something x, or like rather just like a form that fits into trig sub, should we apply it?
Well, unless, all right, so the question is, if you ever you ever see like a constant minus something or a constant plus something under a radical, or something minus a constant, do we always go to trig sub? Well, not necessarily, right? I mean, if there's like a u sub that you can just make directly, sometimes you'll have a remnant factor of x on the outside or something that fits perfectly with being the derivative of what's inside. You want to do that. And by the way, it's not always a radical either. You saw examples in your homework where it wasn't like always a square root. Sometimes it was actually raised to, some fractional power like 3/2 or something. But you just know that that you have trig substitution in your back pocket. And you can say, well, I don't see immediately how to do this, so I'm going to try it, see what happens. And a lot of times you'll find that it ends up being successful. But of course, it can get pretty nasty at times, right? And one thing I noticed, like on the quiz especially, is sometimes it gets sort of gnarly at the end too. Like you want to go back and you have to say, oh man, what was the double angle formula, right? I have sine of 2t. I don't have sine of t. I have sine of 2t. But I know what sine of t is, but I don't know what sine of 2t is. Well, then you use things like the double angle formula, you know, when you make a little reference triangle and then you get it, okay? Other questions? Yeah.
Would you ever create a problem where you have to require trig substitution in the numerator and then the inverse trig in the denominator that we did?
And would I ever create a problem? Okay, because, right. Would I ever create a problem where you do trig sub in the numerator? And then
the substitution we did on the last quiz, we call that the bottom in our denominator.
The denominator.
We had to create a reference triangle and substitute for the denominator.
Oh, well, creating a reference triangle is pretty standard for trig substitution. Like you oftentimes have to end up doing that, creating a reference triangle. That happens quite a bit actually. So I mean, unraveling something by having to make a reference triangle at the end, that's something that, yes, you should be able to do for sure. Okay, other questions? Kara. $8.7. Okay, let's see. Well, if I just do one from 8.8, it'll probably force us to do something like we did in 8.7. Okay, so for instance, oh man, I don't know, let's see. Oh, how about 85? This one right here. How was I able to zoom in on this before? What did I do? What was that? Oh man, now that thing is tiny. What did I just do? Boom, there it is. Now it's not tiny. Okay. Okay. So let's see here. Integral from 1 to infinity, logarithm of x over x squared dx. Now, here's the thing. Let's kind of think intuitively about what we might imagine that this thing would do. Okay. So logarithm is going to be defeated by any power of x, no matter how tiny it is. Yes. So for instance, I could take logarithm of x over x to the 1 or x to the 1 over 1 billion. And the x to the 1 over 1 billion is still going to destroy logarithm. Does that make sense? So actually, I could peel off a tiny amount from the x squared and still have x to a power that's bigger than 1. Why? Why would I care about that? Do you guys remember? 1 over x to a power bigger than 1. What did we discover was true about that when I integrated from 1 to infinity? What happened? It actually converged. Do you remember that? And I have logarithm of x over, I could take a tiny fractional power of x, and that thing is still going to go to 0. So that means that thing is making it smaller overall, which is going to make it converge even better. So overall, my suspicion is that this thing will converge, but let's see why, practically speaking, that happens to be true. Okay? So let's see. Integral logarithm of x over x squared from 1 to infinity. Well, what do you guys think? How are you going to integrate that? So that's like the integral from 1 to infinity of x to the minus 2 times logarithm of x dx. Do you know how to find an antiderivative of that? Integration by parts? Okay. So let's see here. What would you put u equal to? Logarithm? What about dv? X to the negative 2 dx? What's v going to be? What is the antiderivative of x to the minus 2? Negative 1 over x, right? Negative x to the minus 1. And what's du? Oh, that's curious. Okay, so we integrate by parts. It's going to be u times v, which is negative logarithm of x over x. And this is weird, but it's evaluated between 1 and infinity, right? Minus, okay, so hang on a second. So minus, and there's a negative sign right here, so it's plus the integral from 1 to infinity, 1 over x squared dx. Let me ask you a question. When I write something crazy like this, like integrated between 1 and infinity, what do I really mean? What do I mean by this? I mean to take what? Limit as x goes to infinity, yes? What's going to happen if I take the limit of log x over x as x goes to infinity? It's going to be infinity over infinity, but what's going to win? X. So what's that going to be overall? It's going to go to 0 as x goes to infinity. Does that make sense? Because x is going to destroy logarithm. Now, what happens if I plug in 1? 0, because logarithm of 1 is 0. Therefore, this entire thing right here, what does that evaluate to? 0. So in the end, we get that this is equal to, this is sort of weird, this is equal to the integral from 1 to infinity of 1 over x squared dx. Holy smokes. Okay? Those two things have the same value. And what is the antiderivative of x to the 1 over x to the 2? Negative 1 over x. And now I'm evaluating between 1 and infinity. I'm kind of sloppily going through this, but what do I mean? Once again, that means I'm taking the limit as x goes to infinity. What happens if I take the limit of that as x goes to infinity? I get 0. Minus negative 1 gives me a value of what? 1. So what does that tell you about this integral? This thing converges. This integral converges to 1. Okay? What's weird is that integral actually converges to the same value that the integral from 1 to infinity of 1 over x squared did, which is a problem we had done before, actually. Okay? Okay, that was sort of a shorthand way of doing things. Like I didn't write limit and things like that. Technically speaking, I would probably to really make this totally solid, I should probably write limits and things, but that's how you would find the answer to that thing. Okay. Other questions? All right. That's it.